So in part 3 of section 6.1, let's go ahead and talk about F compose G and G compose F for a specific set of functions. So in example 6, we want to show that if we take F and compose it with G, that we'll get G compose F. Now that doesn't happen every single time. It does, but it does not, because we've seen that. And that's going to be equal to X, but this is when F of X is equal to 2X minus 6. And G of X is equal to 1/2 times the quantity X plus 6. And this is actually leading into the next section, the specific problem. So it's kind of why we need to make sure we do it. So let's go find them one at a time and see what happens. We're going to go find F compose G of X. So that would be F of, and now I'm going to pick up G of X and put that right there, 1/2 of X plus 6. Okay, so we're going to take that guy and replace our X with it. So the F function, we're replacing that X. So I would have 2 times 1/2 times X plus 6. Okay, now all I did is replace that X. I still have that minus 6. And we're going to clean that up. So be careful with your order of operations. Very, very important here. The first thing we're going to do is distribute 2 times 1/2. That's going to cancel. So these guys are gone, and I'm left with X plus 6 minus 6. Well, X plus 6 minus 6, the 6's cancel, and I just get an X. Huh. Okay. Now let's go find G compose F. So G compose F of X. So that's me finding G of 2X minus 6. So I'm going to replace all the X's with the F function, which is 2X minus 6. So that would be in G, we're going to do 1/2 of 2X minus 6. Make sure I do it in the right order. And then plus 6. So notice that the X is inside the parentheses. So that means the 2X minus 6 had to be inside the parentheses plus the 6. So there's the plus 6. Okay, well, this time the 6's are going to cancel, and I have 1/2 of 2X. Well, half of 2X is also just X. We did get exactly what they said. When we did F compose G, we got an X. When we did G compose F, we got an X. Another thing to note, which is kind of quirky and kind of neat, is when we did this, when we did F compose G, the 2 and the 1/2 canceled first, then the 6's canceled. So we did the multiplication, multiplication and the division were canceling, and then the addition and subtraction. Well, down here, we canceled the subtraction and addition first, then we canceled the division and the multiplication. So in other words, I got rid of the 2's, then the 6's. I got rid of the 6's and then the 2's. So the order in which things happened were kind of the opposite order. So very interesting to note. If we were to talk about domains again, because these are both linear functions, the domains would be all real numbers, and the domain of the composites would also be all real numbers. Sometimes when you're working with compositions, you need to break the resulting function back down to its beginning parts. I like to call this decomposition. So example 7 is an example of something I call decomposition. Sounds like we're in biology. Okay, what does that mean? Well, what we want to do is we want to find two functions, F and G, such that F compose G is equal to another function, H, and specifically in this case, where H of X is equal to 1 plus X squared, quantity cubed. So, okay, what is that? Well, I like to do this in a pretty cut and dried way. We're going to let G of X be the inside. It's the input function, so it needs to be the one on the inside. We're going to let F of X be the outside, because it's the one we're plugging into. And this works really well with what we used in terms of transformations and the words inside and outside there. So it works really well with that. Okay, so G of X is the inside, F of X is the outside. So what does that mean for us? Well, when we take a look at what H of X is, we can clearly see that we have an inside and we have an outside. So my inside and my outside. So we're going to come in and let G of X be the 1 plus X squared. We're going to let F of x, the x to the third. Since we have to have something to plug into, we have to have a placeholder, we'll use that x. The cube is coming from that outside. So what should happen, this is my answer, I'm done. If I come in and compose these, if I do f compose g, I'm going to pick up this function, the 1 plus x squared, and plug it in for this x, and I'll end up with h of x. Now, this isn't the only answer. It would also have worked. So another possibility would have been, well, what if g of x is just the x squared, and f of x is 1 plus x cubed? So if I really go inside and let my inside function be the x squared and the outside function be everything else, then sure enough, if I plug this g of x into this x, I'm going to end up back where I start with h of x. So it definitely works, but you're going to notice that answers may vary depending on what you pick. Don't ever pick g of x as x. That's not very exciting, not very original either. So, and finally, our last example for section 6.1 is an application, just to show you that it does happen in the real world. So example 8. The surface area of a hot air balloon is given by S of R is equal to 4 pi R squared. So R is the radius of the balloon, and S is its surface area. So if you need to know how much material you need to make your balloon based on its radius, this would tell you that. They also give me a second function. If the radius is increasing with time, so imagine blowing the balloon up. If the radius is increasing with time, according to the function, R of t is equal to 2/3 t to the third, where t is the time that you've been putting air into the balloon, and R is the radius. The radius is in meters, the time is in seconds. This radius is the same radius in meters, and the surface area is in square meters. Just to put the units up there, we don't really need them, but it's nice to see them. Okay, what they want me to do is find the surface area of the balloon as a function of time. Well, I have the surface area in terms of the radius, and I have the radius in terms of the time. So to find the surface area in terms of time, what they're really asking me to do is to take S and compose it with R. So they're asking me to plug up R and plug it into S. We can do that. So we are finding S of 2/3 t cubed. So that would be 4 pi, and in place of this R, we're going to plug the other function. So I'm going to have 4 pi, and now we'll have 2t cubed being squared. Sorry, got to plug in the laptop. So all we have to do is clean this up. We're going to square everything. So we'll have a 4 pi, 2/3 squared, 2 squared is 4, 3 squared is 9. And t cubed squared is t to the 6. When you raise a power to a power, you multiply. Okay. Cleaning it up just a little bit more, I'm going to have 16. That's the 4 times the 4. I'm going to have the pi over 9 t to the 6. And there it is. So now we have a function that is the surface area in terms of time. So now I can tell how much material I need depending on how much time you've been plugging or putting air into that hot air balloon. I think another example that makes a lot more sense in terms of the composite functions is just imagining if you're traveling. This is not on the handout. This is just me talking. Imagine you're taking a trip and you're actually going to France, and then you're going on to Japan, to Tokyo. So you're going to Paris and then to Tokyo. So what would happen in terms of your money is you would take your American dollars. So my first input is the American dollars. Dollars. You're going to put it into some type of machine that changes your dollars into euros. So now you're over in Paris and you're using a euro, and I don't know what the symbol for euro is, so we'll just write it out. Okay, so that was the first function. This would be my g of x function. Okay, well, what do you then do? Well, you're done in Paris. You're now headed to Tokyo next. So you don't take your euros and make them back into American dollars. You're going to take those euros, you're going to put them into another machine, and you're going to get out of it the Japanese yen. So this would be our f of x. So you've taken the output from the first function, which gave you euros, the currency translation, right? And you're then going to take those euros, put them into another function and get Japanese yen out of it. So the overall composite function would have taken your American dollars and made them into Japanese yen. So there's an example of where you use composite functions in the real world. And there's lots of examples. I just think this one hits almost everybody if you've ever traveled. So, and that wraps up our section.